Okay, thanks. Nice to be back after about 5 decades. I was a student here, and then I was also a tutor. So here's the framework that we'll be using today, and in this lecture, and it's almost identical to most of the other, almost identical to what you've already been looking at. Discrete time, either infinite horizon or finite, choosing between cap J, different kinds of choices each period. They're just setting an indicator function, that's the little d equal to 1 if you make a given choice at a given time, or 0 otherwise. So obviously the d's sum up to 1 at each point in time t, and they're either 0 or 1. For now, we'll just assume that there's a finite state space, so there are big X elements in it, although nothing that I say really is confined. It really depends on that assumption, and you'd have to be doing some smoothing, doing some non-parametric conditional estimation of the CCPs, but apart from that, that really doesn't make much difference. The epsilons are associated with each choice at each time. So it's going to look something like a logit model in the end when we put the type 1 extreme value assumption on the epsilons. The data consists of a bunch of choices and also the state variables. And in that sense, there's what we'll call a mixed density function that determines how next period state variables and next period's epsilons are determined conditional on this period state variables, this period's epsilons, and the choice that the person makes. So that's pretty much the setup we've got. We are going to assume in this lecture the conditional independence assumption that John introduced to the literature for the dynamic discrete choice. There were couple of papers before then that did not use that assumption, and as a result of the epsilons not being independent, that conditional independent assumption being violated, you're into multivariate integration, because next period's epsilons depend on this period's epsilons, and this is a key to bringing it back to, in the end, making this look like a static discrete choice problem in some sense. So you can see that next period's epsilons depend on this period's states variables, but the transition function, we'll be exploiting this, especially next lecture after lunch. The next period state variables only depend on this period state variables, and they're all observed. So that makes things a lot more empirically tractable than a situation in which next period state variables depend on unobserved stuff this period. Gonna make this work if I can. Seems to be frozen. Let's see what we can do it that way. No. Oh. Right, that way. Or that way. No, I'm still stuck. Try that.
It's working on it.
It works on this one, okay.
Where's the
Clicker? There. But anyway. Okay, well, I can make it go here. Good. Technical glitch. Have you got here's my, if you can get something there. So far as the payoffs are concerned, discount factor, we often assume that takes a given value, for example, 0.95. It's really a mistake. Our models are incredibly specific to the problem that we're looking at.
Bob, it does work. This is forward, this is back, and this is pointer.
This is the forward, right? Yeah, it wasn't working a minute ago, but maybe your touch. let's move back. Where are we? Okay. Yeah, this discount factor is specific to the problem. And I think, you know, saying that the interest rate is not 5% or something, it's kind of like almost a default thing that we use, but probably not relevant for many cases. The trans-fatality condition is just there so that we don't try and add up negative infinities to positive infinities, just to keep everything in. And then you can see from the way the utilities are set up here in a very standard kind of way, it's more or less additive, well, is additive across the periods, which really means all the dynamics has to be pushed through the x's. And so you're saying whatever dynamics we have is coming through something that ultimately we're going to observe. And that's, again, not something that we really like doing. But if you don't do that, you've got to be integrating over where we could be and where we could have visited in the past, etc. So the next thing to think about in this setup is to say, imagine these people are solving this problem optimally. I'm not even concerned whether they behave optimally or not. What I want is a situation where the patterns in the data mean something to us. And if they're not behaving optimally, that's fine, but tell me how they behave, please, and try and justify it with some axioms if you can. The point about revealed preference theory is it provides a reason for taking the data seriously enough so that we try and uncover what was motivating people when they take the behavioral norms that they take, okay? So that's the justification for whether people behave optimally or not. I'm not really interested in knowing whether they can do dynamic programming or calculus. What I'm interested in knowing about, because that's what we do to try and help us understand what they do. But when I teach my business students, I'm not trying to teach them calculus. I'm trying to get them to understand a little bit more how they solve their problems before they get employed by somebody who says, you learn nothing at business school, this is how it really works, which is what they do, which is what the employers will do. And that's okay, because I'm ultimately saying, guys, you're going to look like neophytes when you enter, but the minute the regime changes, that's where you come on strong, because you will have a framework for being able to analyze what happens when the regime changes. That's what we do in structural econometrics, right? We're looking at patterns, trying to explain how people behave, why people behave the way they're doing, so that if there is a change, we'll be able to provide some guidance, hopefully, as to where things might go then. And that's why they pay us. All right. So the value function is defined for the decisions that they're making now, given that they're optimal. And we define the conditional value function as just being the systematic part of utility that ultimately we're going to estimate for the current stuff, plus next period's value function discounted by beta. That leads us to the conditional choice probabilities that are central to thinking about estimating problems this way, which is just the expected decision conditional on the state variables that are relevant for the agent. So again, if there was unobserved heterogeneity in there, we wouldn't want to define the conditional choice probability on the basis of the state variables we see. We would want to define them on the basis of the state variables that are relevant for them. And hence we wouldn't be able to get sample analogs. We'd have to do something more complicated in order to move forward on this kind of method of estimating. Just before we move on, to thinking about these CCPs, let's just note that when people play a Bayesian game, non-cooperative equilibrium, okay, they're all optimizing. They are best replying to their environment, which includes the other players. And so they're solving essentially the same dynamic optimization problem, but instead of treating everything else technology, they're also including the fact that everybody else in this equilibrium is best replying. That's what's relevant to us. That's all we see. We don't see people playing off equilibrium paths by definition. And all our inference has to be based on the fact that these people are behaving in a systematic way for us to be able to make sense of what they're doing and hence be able to estimate counterfactuals that might help them. That's what identification is about. If we can't do that, we're sunk. That's like saying the data is not good enough to help us to make predictions about what's going to happen somewhere else. Train yourself to be a priest or something in that case, because as scientists, we're trying to use the data to be able to say something about a regime that we haven't seen yet or rarely seen, something like that. So in a dynamic game, there are a bunch of players. They're all making their decisions. There's a transition probability for XT now standing for everything that's relevant in the industry, including my state variables, your state variables, whether we've got the same utility functions or not. And I might be controlling part of those state variables. You might be controlling some of yours. Or maybe I take an action, they affect everybody else's, you know, pollute. That's also possible in this kind of setting. But in any event, we'd be thinking about the transition probability associated with what happens to the state variables next period when everybody else, say, plays their own thing, and I'm little I, and I do my thing, J. Okay. So in this setup, there's going to be some discounted payoffs. They're going to depend on my utility is going to depend on the state variables for the whole, I'll say, industry. There will be an epsilon associated with my particular choice that the econometrician is not going to see. The epsilons typically are assumed to be IID for the same reason that they're assumed to be IID in the individual optimization case. And in this setup, we assume that there's incomplete information in the sense that I can't somehow infer what other, even in equilibrium, I don't see work out retrospectively what the other people's epsilons had to be. Not a complete information game. In other words, I don't see what other people do right now, okay? And as a result of that, I'm going to be integrating over what they might do because I see I see the X's, but I don't see their epsilons, okay? So in this setup, just as the same as in the single agent case, we've got conditional choice probabilities where I'm asking myself, what is everybody else doing? Well, I'm just looking at the state variables in there. I'm asking myself, what do they do? This is just going to be this probability that they take these actions, okay? And in this setting, since Victor will be doing this in more detail tomorrow, let me just note that the individual optimization, when the individual optimizes, we can think about the kind of a reduced form utility that's associated with the utility that I'm going to get when everybody takes their individual action. I don't know what action they're going to take, so I take a probability that there's a probability that they'll be taking this action. And then I'm just summing over all those probabilities to get an expected utility that I get from taking action J when I'm Mr. I and I take action J. Okay. And notice that this U here is going to be augmented also by that epsilon in an additive way. And in that setup, this utility is going to be exactly the same as the dynamic, the utility that I get from the dynamic optimization problem when I'm the only player in it. And this transition function is just, here is the transition function I get when I take action J. The state variables were x, xt, could be I, maybe it's the the variables for everybody here, okay? Maybe because depending on how much I see of everybody. And then I'm just going through and looking at, well, what's the probability that we reach xt plus 1 when everybody does this action, and then of course, and then again, they have these probabilities that they are actually taking of getting those outcomes conditional on those actions. So in this sense, these two guys match in exactly with what's being solved in the dynamic optimization problem. Notice that I'm just talking about the problem that each individual solves, and I'm emphasizing the equilibrium actions of everybody else, because ultimately what I'm concerned about is the inference I can make given that everybody else is behaving optimally. I cannot do any more than that. If I go any further than that, I'm saying something about what is not seen, which is fine. Go ahead and make up stuff if you want. Politicians do it all the time. But the issue is, what can you actually get out of the data, and how far can you move ahead on that? So the starting point for this analysis is to define differences in the conditional value functions. Think about what's really being solved here. Maybe I have it on the board, I should. You've got an epsilon associated with a particular action. You've got a conditional value function associated with that. You're going to choose the biggest one of those. All right. Now, when we're thinking about what people do, we don't care about what utility they have, nor do we know. Well, all we can do is infer from what they do the choices they did not make. And so it's natural that you would be thinking about differences in conditional value functions that arise from the fact that this person might have chosen little j instead of big J. Okay. So this gives us the conditional choice, the CCP, I'll just call them that in future, is obviously just going to be, and you can sort of bring these around, it's just related to the fact that Vj plus epsilon j has to be bigger than little vk plus epsilon k for all the k's in order for this to be, in order for action j to be chosen over all the other k's. And that really means then that we're just going to integrate over all the things that we don't see, namely the little epsilon j's and epsilon k's, in order to work out what the probability of taking action j when the state variables are x. Okay, so that can be written down in terms of, this is just a little bit of intermediate statistics, just taking, or definition of a cumulative distribution function, looking at integrating over all the epsilon j's where we're plugging in the delta v's in the bottom there. So let's think about this just a little bit further. I want to define this Q function to be equal to the integral over this epsilon j Let's go back one. Where does this G come from? Here it is. Okay, just the derivative, and we're plugging this in. We're just taking that GJT. This thing is just the probability of taking action J in a static model. Okay? Well, that's not really very surprising, because in the dynamic model that we were looking at a minute ago, all we had were delta V's instead of delta U's without, with a logit or something. You'd have a delta U without a T there, okay? That's all that's involved. Well, I say logit. Really, for arbitrary distribution function, that would be the form that it takes, and then the logit simplifies from there with the type 1 extreme value. In other words, static random utility model. All right? So here we have our static random utility model, where the payoffs are delta J plus epsilon J for the jth alternative. Just going back to McFadden, all right? And we're defining QJTs that way. And so let's just put the vector together. Point 1. These delta V's have a one-to-one mapping with these P's. In other words, the inverse of Q exists. And that's really saying the following. Think about what people are choosing here. They're choosing the best thing for them. That just means the best out of what they have available to them. We see the probabilities of them making those different choices. We're asking ourselves, what can we work out from that? It has to be, mathematically even, that those delta V's are really closely related to the CCPs. And intuitively, the higher the VJ, the more likely you are to choose action J. No surprise. In the case where there are only two choices, it's obvious. In a case where there are more than two, little less obvious, but still true. Okay? So that's what we mean by this inversion theorem. So now we have that the CCPs are related to the differences in the conditional value functions. By the way, suppose these CCPs were independent across time and people. What more can the data tell us than the sample analogues to the CCPs? Short answer, nothing. They are sufficient statistics. The CCPs are sufficient statistics for the data. And so in that sense, the CCPs are just a first step to summarizing the data. If you've got billions of observations, you need to go through some data reduction exercise. Maybe you should use sufficient statistics before you start imposing a whole bunch of other stuff on it. Now, this is me speaking, not necessarily agreeing with everybody or them agreeing with me, but that's my personal opinion, so I should keep my voice low. But in any event, that's the sense in which these CCPs are potentially important, and the inversion theorem basically says that using math language. Let's define the conditional valuation correction then as what we'll call the social surplus function, that's the cap V, minus a conditional value function. Stationary settings, you can just drop the T, of course. T doesn't play a role. And ask yourself, well, let's have a look at this lifetime utility. It's expected lifetime utility would be if you committed to action J straight off. Suppose before you see the epsilon J's, you think, okay, I'm going to take action J. That's clearly not optimal, but we're just talking model talk here for a minute. What would be your expected utility then? Well, it'd obviously be the conditional valuation function plus the unconditional expectation of the epsilon J. There it is. So if you were to take the action before you saw the epsilon rather than after you saw the epsilon, which is what you do when you're solving the problem. I mean, the latter is what you do when you're solving the problem, then you would make a loss. And the loss that you would make is just equal to this psi function minus the unconditional expectation. Unconditional in the sense that it's just the expected value of x on x without the selection aspect. So for example, and this is not true for logit, if this thing was equal to 0, this loss that you would make would simplify to psi jt. So that's why we call it the conditional valuation function correction. Now, this is just a piece of notation that's going to be useful in thinking about how to characterize the social surplus function. It's not of use to anybody who is actually in this game or optimization problem solving it. They don't care about this. We care about it because it turns out to be helpful to us when we're thinking of estimating, or at least at minimum, identifying these kinds of models, okay? That's why we care about the size. Of course, we're economists, professionals, researchers, blah, blah, blah. So, capital V. Yes, capital V is the expected value of my lifetime utility before I see my epsilons, but knowing that I'm going to behave optimally all the way through life. Yes. And everyone was type 1 extreme. So, just an example here. The value function correction, just nested logit. Well, then that's what it would be. Okay, that's what this correction would be. So, for example, if there was no correlation between the different alternatives, the sigma would wash out, and you would left with Euler. This is Euler's constant minus log p. Okay, so that's one way of thinking. That is a convenient sort of benchmark case because the type 1 extreme value is the one we use all the time. And so the conditional value function in that case is just going to be Euler constant minus log p. The Euler constant is always going to wash out. And so, effectively, you're always going to be thinking about minus log p. Yeah, there's a question there too. Yeah.
Is this a property of the value distribution, or is it just a general theorem that applies to any?
Good. This is specific to the type 1 extreme value distribution. The general point is that this psi will only depend on the x's directly if the disturbance itself comes from a distribution that's conditional on x. So for all we'll say independent distributions where you don't have the disturbance, that epsilon thing, depending on the x, then this psi function will only depend on the conditional choice probabilities themselves. In other words, all the dependence on x will come through the piece. So that's the sense in which if you have dependence of the disturbance on on the x's, so the g functions depend on those x's, then they're expressed, then you'll know exactly what then you'll know what the nature of the dependence is because of the way you've specified the g, and you'll be able to work out what the psi is in that case too. So there's no dynamic programming involved in getting the size. It's always, in the independent case, it's always going to come through the CCPs. And in addition to that, if there is dependence on the x's, it'll just come through the way you've specified the disturbance term for that period. For that period. For reasons that'll become clear later, I haven't included that kind of material on the slide, on these slides, but that's the answer. So notice, for example, here I haven't got the epsilon depending on the x's at all, and that's almost always the case. And we have to think about, gee, why is that the case? We'll get there. So let's think about telescoping this conditional function just one period form forward. Okay. Here is our conditional value function. And here is next period's social surplus function. Hitting it with our beta. We're integrating over this. The transition function is j because we're taking the jth action right now. Okay, that's by the definition of the conditional value function. And now let's go to our previous slide for a minute. Actually, previous two slides for a minute. And look at this guy. See that? Vt is equal to Vjt plus psi jt. All right, put a t plus 1 there instead. Okay, same equation. Move it down further. Plug it in here for any k, any action. Meaning we could have had the value function in here. This is the thing from doing something optimally. Well, why don't we just write that in terms of this non-actual picking k instead of the right one and then having a value function correction. Put it in there. And this comes back to your question about what does this really depend on? And is this easy to calculate? And of course, I took about 5 minutes to explain, yes, it's dead easy to calculate, all right? For a reason. And if we just move on just a little bit further, because after all, this one here has that kind of representation with t plus 1s there, expand it out. See? I'm calling it telescope, all right? Just push it out. Do a little bit of algebra. And I said you could pick any of these actions, including any combination of these actions, including not just putting positive fractions, positive values on those fractions, the omegas, but I could have negative ones too, providing they sum to 1, who cares? Trivially, the sum of the VKs, if they're weighted with their corrections, is going to equal that big V as we push out towards the end of the horizon, providing these sums are equal to 1. And also, again, let's keep things bounded on both sides, please, just so that we can talk about adding things up and subtracting them. Okay? And that's all we require. So look what we've got, guys. We've got the conditional value function. Remember, it's the epsilon plus the conditional value function that these guys are optimizing. You know, in a discrete choice model, it would be the epsilon plus the u. Now we've got the epsilon plus the conditional v, right? But the conditional v is just the sums of stuff. You can see that there's this correction aspect going on here. all right? And there's some weights. Those are the weights. What is this kappa doing here? Well, think about somebody taking some pretty crazy actions, and who cares? This is us thinking about them, not them thinking about themselves. We've already had the spiel about people being optimal, so I won't repeat that. You've got, what's the chance that I'm going to end up at a particular xt plus 1, given that I took some kind of actions that were determined by these weights? These weights are just telling me which actions to pick, all right? And if we thought about those omegas all being positive, then they would just be like positive probabilities of like a mixed strategy, okay? It's certainly not an optimal mixed strategy, but a mixed strategy if they're all positive. And then we'd say, well, what's the likelihood that we'll end up at state X? Well, I could have taken any one of several several of these things. I don't know which one. Just attach the probabilities for the transition function, reflecting the fact that there was only some probability that I took it, where I am now interpreting these omegas as probabilities for the sake of the argument. This is just a Markov thing, all right? Here I'm just writing down what's the chance that, what's the, I'm going to say, weight that you attach to x tau plus 1, conditional on following a bunch of weights. So really I should have a sort of a superscript omega in brackets up here, because that kappa is reflecting a sequence of weights that I've chosen for each of those actions, positive or negative, along with the transition probabilities that got me to where I am now. So this is the probability that I start out by choosing action J when I'm at xt, that I will get to x tau plus 1, which is an element, tau plus 1 periods later, and that it will be x tau plus 1. Okay, that's all it is. In other words, making sure I pick out my states with the right weights as I move to the future. Okay, that's all it does. So here we have some utilities, some future utilities, some weights of making choices, and some transitions. We can almost plug that into some kind of estimation problem and go, bam, just knock out, parameterize these guys, subtract the little VJs from the little VKs, almost logic model, okay? Getting a little bit ahead of ourselves. What's actually identified? I mean, you go ahead and do maximum likelihood. Did you actually prove that that maximum likelihood isn't flat at the top? Because if it is flat at the top, well, then your model's not identified. It means that there are observationally equivalent data processes that give you the same limit. And the only reason you're getting a maximum is because your sample is jagged. And when you add another observation to it, it'll be all over the place. And by the way, I won't even believe that you've got a maximum in a multi-dimensional setup, because it took forever to discover that Everest was the highest mountain. And that's only 3 dimensions. So that's the sense in which, and I know I'm treading on very dangerous ground here. I'll just run to the door. That's the sense in which at least getting a first round set of consistent estimates using, I'll say it one more time, a set of sufficient statistics is a reasonable way of going when you're thinking about actually estimating these kinds of frameworks, as opposed to starting someplace where you have no clue what the parameters are. Okay? So we can talk about small samples if you want, but it's the alternative. So here's our setup. We've got these conditional value functions all that way. What is identified? Well, let's imagine we've got the conditional independence assumption, we've got the x's and the outcomes. First thing we notice is that if we appeal to the inversion theorem, the policy function itself is identified. Now let's have a closer look at this before you all start going around estimating using BBL. Seriously. The reason why this is identified is because we're using the inversion theorem, which is obviously dependent on the functional form of the epsilons that you've already baked into your model. Put it another way, the model is not identified if you don't say what the distribution of the epsilons are, and don't put any other restrictions on them. Now you can. There's nothing against the idea of putting restrictions on the way the observed variables enter. And in fact, that's probably a good way to proceed, because you can see how the observed variable vector enter, and so maybe that'll help you say something outside the data that allows you to put the restrictions on the way the observed variables are affecting the choices that people make. In other words, affecting their utilities, and that will allow you to relax something about the distribution of the epsilons. And the reason I'm mentioning that is not because I just like jabbing at my colleagues in different ways. The reason I am, not just because of that, the reason that I'm saying that is that when we get to discussing unobserved heterogeneity next lecture, I'm going to have to say, look, we should know something about how these x's enter the utilities in order to make any headway at all in being able to estimate unobserved heterogeneity. Yeah, go for it.
Okay, so the already needed the x.
Yep.
The seed is not an individual, they're all at every state, for every individual.
Let's come again. We've got, yeah.
Aggregated the data effectively.
Yes. Even given that assumption that we've got a set of x's that we observe, pushed all the other potential x's aside, we still need a parametric assumptions on those epsilons, type 1 extreme value, for example, that are going to enable us to go ahead. So yes, absolutely agree. We've already made a ton of assumptions in setting up in slide 1 and 2 or whenever it was. That is just basic, I shouldn't say just, but that is the sense in which we scientists are unfortunately limited by our crappy data. It really means that that's all we can contribute as scientists. As politicians, go ahead. But as scientists that are trying to infer from what the data can tell us, that's where we're limited, okay? Point is here that this policy function is really identified if you make the set of assumptions that we made before, okay? And the reason, I guess, for your question, Ashley, is that there is a sense in which you read this other literature and you think maybe that this thing is identified or can be estimated even if you don't make an assumption about the epsilons. That's just wrong. So I shouldn't have this on tape, but anyway. But anyway, it's still wrong. So this is the sense in which, given parametric assumptions on the epsilons, given the x's that we've already said, we're good. This policy function is identified. And notice it doesn't just depend on the x's, but it also depends on the unobserved epsilon, obviously, because policy functions depend on what the people see. So as a result of that, we can then go ahead and show that the conditional value function correction, is also identified. Why is that important? Let's go back here. Sorry, I'm moving the wrong way. Yeah, here we go. I'm going to claim that each of these guys is identified too from the CCPs, given what we talked about before. Okay. Why is that? Again, just running through this slide, just looking at the difference between the surplus function and the conditional value functions. Well, I've worked through the algebra here, and all I'm doing is using the inversion theorem in a couple of spots, pulling it in, integrating over the G's and going for it. Okay? I don't expect you to follow the lines right now, but you've got the slide, so that's good enough. Okay? So that's identified. So now we have that these guys are identified. Okay? And we can write the utility function, small u, as equal to what we'll call a reference utility function. I'll come to that in a minute. As well as, let's see what's left. Here are some things that are going to depend on the CCPs in the way that I described before. All right. Here are some, I'm going to call this future reference utility functions. Okay. And the kappas, they're just defined by those transition probabilities estimated outside the model, offline, people say. Everything's offline. With the transitions and also the weights that you've chosen. Okay, you've picked any set of weights. So this is all a number. This is a number. Beta, I said at the beginning, it should be application specific and estimated. Now I'm backing off that and saying, okay, let's just set it at 0.95 for a minute. It would just give you a little bit of leeway here. So that's a parameter. And then you've got this guy and these reference utilities and other numbers. Well, okay. Reference utility. You all know that in a static model, you're never going to get U1 and UJ all the way out. You only get the differences, obviously. You're always norming relative to one of the reference utilities. And the same is true in dynamics. And in particular, you've got an exactly analogous result. It's exactly the same thing. You've got to have a reference utility for the last period, the second last period, blah, blah, blah. Okay? So we'll just call that the reference, the action associated with the reference utility, action 1. And so actually, these guys can be set to 0. See that? And now you've got this utility is just equal to a bunch of numbers you've calculated and a beta that you plugged in the right spots. Done. Forget the dynamic programming. Dynamic programming is incredibly useful for computing counterfactuals. No question about that. In addition, dynamic programming is incredibly useful if you want to squeeze that last piece of efficiency out of your model, especially if you're lacking observations and you want to impose that extra structure on it, given that you don't have a whole lot of data. This is the projection you want to make. And if you don't do something like maximum likelihood, everything will turn out insignificant. So don't get me wrong, I don't want to overstate my case here, otherwise I'll get killed, but also I don't believe it. Dynamic programming and that kind of stuff really helps in those kinds of situations. But what do you got a ton of data? Why wouldn't you summarize the data in some way and then use the CCPs and the transitions as you kind of move forward? Okay. So again, us lecturers get on with each other for many years. 40 years. That doesn't mean we agree about everything. Almost. So that's the representation result. And in a stationary model, we have a similar kind of setting. Now we're just putting everything in matrix form. Okay. You just care about the states, stack them all for the transition matrix, go for it. Solve directly. See how it enters here? With the correction terms. We're done. So if we didn't want to impose any more assumptions, and this is getting to Ashley's question. Thank you. It's almost like I scripted you. We got these conditional choice probabilities, which, if we have reams of data and relatively finite number of states, so we can get them all, well, then we just could take cell estimators. Likewise for the Fs. And then I know Bertel almost always stops me and says, what if we've only got a few states, a few observations on this one? You're cooked, Bob. Do my method instead. That's what he means. And he's right. But can we go any further than that? Well, obviously, if the states are connected in some way, they're not categorical, but you're thinking about something where you're approximating things in years or something like that. Well, then you're going to take the years nearby, right? You're going to exploit continuity. And in that way, you're going to do something like a non-parametric estimator for the P's and potentially for the S. It'll only work if you don't have, if your variables are not categorical, if there's a way in which you can talk about closeness, okay? If there's not a way of talking about closeness, excuse me, then it's going to be more difficult to think about, to think about this. And then there's an issue is, do you want to use that as data? Do you want to treat it as unobserved heterogeneity? I mean, those kinds of questions start to come up. No issue there. But let's suppose you can get these cell estimators, and notice that they're not the things you ultimately care about. The whole point of econometrics is to be able to take a large amount of data and then consolidate it, summarize it in such a way that other people can use it. And so you're ultimately not concerned about these estimates of P's and F's, of course. You're ultimately concerned about, I'm going to say, elasticities that would come out of counterfactuals. You're not even concerned about the U's, really. And so it's really the U's that go into your predictions and how people change their behavior that you're ultimately concerned about. You know, back in the, it's awful for me to say this, when I was a graduate student, so I won't use the years. Let's just say that Tom Sargent was sitting in the class. He was still a full professor though. Lucas's class. We were talking, not me, they were talking about primitives. And what they really meant was things like the utilities that go into the optimization function or the game that then provide the equilibrium behavior of these people. That's all very nice for economists that get Nobel Prizes and lots of NSF grants. The rest of us have to produce results that are of interest to students or future researchers or somehow add value in that way. And that really means the kind of policy stuff that we do is really concerned about the counterfactuals themselves. People want to know, where did you get this counterfactual from? Show me the steps. And that is the motivation for doing structural econometrics in the first place, as opposed to just say, look, I'm from MIT, just believe me, that's enough. Unfortunately, I'm not from MIT, otherwise that's probably what I'd be saying. So that's the, I'm just talking about myself, of course, no one else. So in that sense, you want to be able to say, this is where the data comes from, this is how we use it, and these are the results we get, okay? But at the same time, people are only marginally interested in the actual parameters of the utility function that you estimate. That is not something that they care about, and it's going to be something specific to the model. Just like I said, that the betas themselves, those discount factors, those subjective discount factors are also going to be sort of specific to the environment that you're actually looking at. For example, you're looking at people that are practically old age pensioners, or you're looking at people just starting their career and thinking about the future. Okay, maybe they have different types of betas. I don't know. So having got these, you just plug this in here, you get the utilities out. Okay, straight off. It's exactly identified. In other words, you can't get anything more efficient than that unless you impose actual assumptions on the use. Let me say that one more time. Whoa, sorry, going the wrong way here. Here we go. One more time. Suppose we know the distribution of the epsilons, coupling extreme, nested logit. Actually, not even that. If we know the nested logit, we actually know the sigma parameter, the correlation. Okay. And we have a bunch of x's, and the utility of each u depends in some special way on the x and the j. In other words, you haven't imposed any parametric assumptions on the utility yet. Okay? Then you get this formula out. Okay, here it is. That is the maximum likelihood estimator because it's exactly identified model. Okay? You got as many CCPs as you have conditional value functions as you have primitive utilities once you've normalized in the appropriate way. Now, I mean, the inversion theorem does a little bit more than that because counting the equations and the number of unknowns doesn't quite do it. We all know that. So yes, there is a little more to it in terms of actually getting that in terms of being able to make that set of equivalences. But it's true, okay? So this gives you what are, in a sense, what are the maximum likelihood estimators when you don't put any restrictions on the model aside from the assumptions that I've just said. It automatically means that if you parameterize the model, so you do have restrictions, then the efficiency that you get from coming up with a more efficient estimator is exclusively due to the parametric assumptions that you are putting on the model. Clear? So when you write down, I'm going to do maximum likelihood, it means that you believe the linear utility functions that you put on your U's enough so that you want to improve the efficiency of the thetas that come on off those coefficients. Nothing wrong with that. Let's be clear. But remember what I said about what you're really interested in? I thought it was those elasticities of the counterfactuals. That's what you'd really like to get a handle on. And so then there's a question of, well, how do they translate? And how do we think about it in that way? Now, I'm not going to push any further down that line. I'm just provoking you, okay? In terms of thinking about how to move forward. Well, in practice, of course, we all put restrictions on our utility functions. I am a sinner.
Well, given that we all put parametric restrictions on the utility model and the utility function and all that takes off the model, wouldn't we want it to be those restrictions that you impose when you estimate the CCPs? I mean, you were estimating the CCP parameter, so you ought to do that for inverse conditionality in terms of estimating the non-parametric estimation as you increase the number of state variables. Does the inverse dimensionality become more computational and solve the model? So you have to somehow base either one person dimensionality or the other. And yeah, so what do you think about that?
I'll tell you, since I'm on stage. I think it's a question of how we gauge the different types of restrictions that we want to put in our models. And so to the extent that we really believed, or there was something in the data, say some engineering piece in the data that said these restrictions should be incorporated at the front end, I agree with you. And so the most obvious places where that occurs is in the production function itself, because the transition probabilities, because that's sometimes, well, bus engine. You can actually see what the transitions are, and you know the factors under which it occurs. And so it makes sense to parameterize, for example, the transition functions in lots of situations. Now, the things that we know least about are the way in which the x's interact to form the u's. And so that's the sense in which, not the x's and the epsilons combine to form the u's. And so we typically make assumptions about, well, the type 1 extreme value assumption, which drives, in a very large measure, the efficiency of the maximum likelihood estimator, because it means the V's and the conditional V's enter in a very specific way. So there's a kind of a question here as to, should we be going for something that is more efficient within the framework that we said, okay, we're going to assume this, this, and this, or less efficient in that sense, but saying we need to account for the selection. So that's where those size are coming from, those value function corrections. But we don't necessarily believe that efficiency in terms of asymptotic efficiency is necessarily the most important thing as we sort of move forward. So I think this is definitely an issue for debate, and it's a debate that's worthwhile having in lectures like this one. But that's my answer. Thank you. Also true. We probably will, guys. Okay, so there are different opinions about this. Okay, so suppose in many applications, we have that subjective discount factor is known. And suppose we're now willing to assume that U is linear in X, but does not depend on T. Okay, so it's a common assumption that we make. I'm going to argue to Bertel, because I know the rest of you are 100% convinced of what I said, so I should really be facing Bertel now. That even in that case, it is useful to go ahead and get a consistent estimator of the thetas as a first round estimator for something that you might wish to pursue efficiency-wise later on, either your maximum likelihood or Victor's swapping algorithm that takes a one-step Newton-Raphson-like iterate to get to something that's asymptotically efficient. And the reason is the following. Instead of starting with the planet and then trying to work out which is the highest mountain in the world, can we at least start somewhere in the Himalayas and then go from there? Then we don't have to be comparing South America, Andes, with what's going on in the Himalayas. And maybe if we've got enough data, given the kinds of assumptions that we're throwing on the model anyway, we'll be able to get a reasonably good, consistent estimator of what's going on. Again, we don't really care about the P's. In this case, we might, we might be concerned about estimating the theta in an asymptotically efficient way. Suppose we were. Why do we want to start out all over the place? Should we simply discard the only set of sufficient, not the only, but the most, but a set of the sufficient set of sufficient statistics that are given to you by the CCPs themselves? Okay. So here's one way of going about it. Just go ahead and get your transitions. This is always done in whether you're doing maximum likelihood or not, because really they do maximum likelihood over here, and then you plug the estimates in over there, and then you get the utility functions. It's really a two-step estimator in which you're correcting that first step for the very good reason that you don't usually mix the transitions with the estimate of the utility functions unless there's some unobserved heterogeneity. So people use two-step estimators all the time. That's not the issue here. But in this case, you've got, well, why don't we look at just minimizing the distance? We take these non-parametric, semi-parametric estimates of the U's that are just found from plugging in the CCPs in the appropriate spot. Take, say, a Euclidean norm and hit it, and then minimize with respect to theta. Done again. Okay. So there's going to be in this case, if this is linear, well, these are numbers. This is a weighting matrix, which we pick, and obviously it's going to be, you can choose your weighting matrix optimally. This is by assumption linear. So as Erin will demonstrate, how to do least squares. Other people have written articles on it, as you pointed out. This has a closed form. You get root n consistent estimators for the theta, which you can then do a one-step with Victor if you wish to get them more efficient, or go all the way to maximum likelihood. But here's a set of starting values for you. Or perhaps you could just plug in a selection correction factor. Here you've got something that looks like a logit with a type 1 extreme. You've got the uj up the top. You've got the sum of the uk's down the bottom, all hit with their exponentials. You've all done a logit many years ago, probably by now, even for you. It's dynamic though, so we'd better have these h's in there to correct for the future. People don't just care about the utility they get today. There's lots of evidence to suggest that they actually do make plans. That's why we do dynamics. Okay, and those plans are going to be impounded in that H function. What is the H function? Basically, all these correction factors, some of all discounted correction factors all the way down. Okay, most of you have heard of Heckett's, right? Where you do a selection correction to deal with the fact that people select into different occupations rather than just randomly. Well, here we're doing a correction factor just to deal with the fact that people also care about the future. All right. Or you could take a simulation if you wanted to. And in that way, what time have I got, John?
You're fine. You have 15 minutes left.
Oh, okay. So we'll have plenty of time to discuss. But I'll take other questions too. We have, or you could take even more, or early lunch, which is fine. Or you could take a simulated methods of moments estimator. Okay. And in that case, you could imagine simulating the lifetime paths out using the p-hats. You've already got those conditional choice probabilities, simulate out paths for people. You've got a correction factor that you want to put in. You can actually simulate that as well if you wanted to. And that would then generate future paths. And from there on out, you could just get these estimates in that way. And the way you would do that then is just put together all these simulated paths looking at simulated paths of going one way versus the other. And in that sense, come up with once you've got an instrument vector, which you're always going to need in this case. Instruments could be, for example, the state variables, because people are conditioning on the state that they're in. Then you're just looking at instruments times these differences in value functions when they're corrected for the correction factor. Okay, so that is all I've got for this first lecture. I went through a little bit quickly, I guess, brushed aside too many questions. But if there's any discussion or questions that people want to raise now, this would probably be a good time to do it. Otherwise, we'll just have to tell these people at lunch, get the lunch for us to hurry up. Anything? Professional? Yeah.
Thinking back to your population model for this are.
Yeah. Yep.
It strikes me that you could combine the CCP, a bunch of steps back where you're making fewer assumptions, with sort of the causal inference random assignment kind of literature. You thought that there was a random experimental shock, and you could difference the CCPs effectively. That should identify something about elasticity, right?
Okay. So, sort of yes. Let's think about what's involved here. And the reason it's worth thinking about taking this pretty seriously is because that's the way I really do think that econometrics will go. What we're really trying to do here is work out an elasticity that applies to a counterfactual regime. Okay, that's our goal. We see in the data the sufficient statistics for the CCPs and the transitions that are conditional in the states and the actions. We're going to use those things to be able to get at the elasticity that we want. So here's how we would go. We would be asking ourselves, how are people going to solve their model in the counterfactual regime? Of course, those people come from a population, so they're going to be heterogeneous, and so we're going to have to aggregate in order to be able to get what we'll call an elasticity. Okay. We don't know the problem. We don't know the parameters of the problem that they use when they're solving the problem, when they solve their counterfactual, or indeed they use when they solve the current regime. So we go ahead, and if we're not willing to impose any extra restrictions, we get those unrestricted, exactly identified U's that I was talking about before. And then we ask ourselves, if people had those utilities, what would they do in this counterfactual regime? We would then solve their problem in the counterfactual regime. It's exactly identified, remember. So if we solved it in the current regime, we'd get very good answers. Okay. We solve it in the counterfactual regime, and from the solution that we would get from solving their problems in the counterfactual regime, we would then get put together the elasticity by aggregating across the demographics. And actually, that's the sort of thing that another co-author and I, Natalia Kronenzina, and I did for the IER that came out a few months ago. Okay. But that is exactly how I would imagine us proceeding in that kind of situation. And so we could then come back and say, well, what are the standard errors that you get out of these elasticities? Because they would obviously come from induced by the sample errors that we get when we're putting in those relative frequencies and what have you to get our CCPs and to get our transition probabilities. Clear? So it's not directly taking differences in CCPs. Well, it is, but you've got to be able to solve for the CCPs in the counterfactual regime as well as using the ones that you've got in the current regime. Then the question is, do you also impose the CCPs that you're using in the current, the elasticities or the CCPs, theoretical CCPs in the current regime for the parameters that you estimate, or just the samples? And then it's going to be a question of how many restrictions did you impose on the utilities? Otherwise, of course, if there are no restrictions, you get the same thing back. Fair enough?
Well, I have a question.
Of course.
So you have this really nice result on, if you know a reference, you have to know a reference utility, but if you don't know, then you'll have a generally partially identified model. Could you comment on this work by Calipsidi, Kitamura, Lima on identification of counterfactuals in dynamic discrete choice models when you don't know that reference utility? So the utilities are kind of only partially identified, but you can still identify counterfactuals. Has that been played any role in your work or that their results?
Okay. I have done some work on partial identification in a different context. Okay. Now, I can't comment specifically on what they've done because I haven't gone through it closely enough. But I can definitely, first of all, we can definitely talk about, start out with the epsilons, start out with the G's, don't make a norm assumption, and then talk about observational equivalence. Now, in the stuff that I've done of observational equivalence, we map out, this is us, the Arkano and me, map out the set of observationally equivalent sets. It's an if and only if result, okay? And so you get something out of that. We never pursued that in terms of pushing forward on the counterfactuals. And the reason we didn't, and maybe there's something in their work that we didn't pick up on, quite possibly, actually, almost definitely, that allows you to actually say something, I'll say meaningful or helpful about the counterfactuals. My argument would be that you don't get that much out of it unless you impose some kind of restrictions. But they might not be enough to point identify everything, but imposing some restrictions, and there might be plausible restrictions that you do impose, would still just shrink the set a little bit so that you had, you know, we're talking about the identified set here, guys. Shrink the identified set a little bit so that you could actually say something about counterfactuals. And in fact, if we move to a slightly different literature, very closely related, in which, notice I said, well, these models are exactly identified if you know the G function, the disturbance function, and you're not willing to put parametric stuff on. And I also should have said, if you know the value of beta, okay? So suppose you don't know the subjective discount factor, don't know the discount factor. Well, then your model is still unidentified. And it's easy to see that because you can always set a beta of 0 and then call it a static model and just think that the X's affect the current utility in that way. Nothing wrong with doing that. It's observationally equivalent. And my way of thinking about it, a way of thinking about it, would be to just interpret those current utilities as conditional value functions that you haven't really fully specified. You're just estimating straight off. Okay, so that's the sense in which the literature on, and this is a Chicago guy, John, I've forgotten his name. You would know, 2019 Chicago. It doesn't matter. That's the sense in which you impose other restrictions on how the utility depends on the X. For example, drop the time subscript in and exploit the fact that as you close in on the horizon, the choices that people will make will be different. All right, that's the whole point. Whereas if you've got an infinite horizon stationary problem, that's not going to help you at all, obviously, because utility doesn't depend on time horizon anyway. if you impose restrictions on the way utility is affected by the X's or by the X's and the T's, well, then you have a chance of being able to estimate the beta. And in fact, even in a 2-period model where you drop the utilities being dependent on time, so that you get utility in one period, utility in the second, ends, that model is enough to identify the subjective discount factor for the second period, at least if you satisfy some kind of, I'll say inverse function that will probably work. Okay, but providing conditional choice probabilities are not too far out of whack. So.
Okay, thanks, appreciate it, Dan, yeah. Okay, any other questions? Okay, well, let's have some lunch and return here after lunch.